Creating structures with the mechanical properties of trees like these, supporting their leaves and branches in all weathers, would challenge the best engineer. Add to this the requirement of growth and the continuous need for an intricate network of plumbing to transport water and nutrients throughout the growing plants, and the task would surely defeat the engineer. Often the most severe mechanical stress for land plants is the wind. The supporting and anchoring structures must be sufficiently strong and flexible to withstand tremendous bending forces without breaking, becoming permanently deformed, or being uprooted. In some plants, the emphasis is on flexibility, like these grasses. They bend with the wind and spring back later. In other plants, the emphasis is on stiffness. They withstand the force and are less bendable. We've come to the Royal Botanic Gardens Kew to look at plant structures and consider how their mechanical properties meet these varying needs. One of the reasons for these differences in mechanical properties is simply differences in cross-sectional area, but surprisingly, so is shape. This is a rather floppy piece of paper, but change the shape and bingo, it's much stiffer. So shape is one of the principal factors that determines the mechanical properties of a structure. The other important factor is the material of which the structure is made, and also the way the material is organized. These are two pieces cut from the same strip of paper. Now, clearly, the bottom piece is less stiff. And the reason is because the cellulose fibrils of which this is made become orientated when the paper is rolled during manufacture. So the paper is stiffer along the axis of the fibers. Now, you usually find that when tissues are young, and especially at the growing tips, they're soft, quite flexible, and easy to break. As they get older, the tissues become harder, less bendable, and more difficult to break. They're going woody. The structural material has changed, and these older woody tissues can no longer grow in length. Let's consider first the mechanical properties of the young non-woody tissues, where cells can elongate and grow. The only structural material here is cellulose in the cell walls. Paper is made of cellulose, and it's very good at resisting tension, but poor at resisting compression. So how can a young plant with cellulose cell walls stay upright and resist compression? Well, this chair does a pretty good job at supporting my compressive weight, and the only structural material here is this plastic cover. The trick is to blow it up so that the pressure inside holds the cover under tension. Individual plant cells with cellulose walls do exactly the same thing, and they behave rather like a balloon. A structure like this can withstand compressive forces. If I squeeze the balloon, increasing the pressure inside, this puts the rest of the skin under greater tension, and it accommodates by altering shape and stretching. In plant cells, the reaction between the tension in the cell wall and the internal pressure of the membrane-bound protoplast is called turgor. Turgor gives living cells a degree of structural rigidity, and their shape depends on properties of the cell wall, just as the shapes of these balloons depends on the properties of their skins. But in plant cells, of course, the internal medium isn't a gas, it's mainly water. And it's easy to show that the young parts of plants rely on water to achieve structural stiffness. Wilting shows that water is very important for the support of young shoots. Return it and they revive. In fact, the overall pressure of the inner tissues, due to the turgor of individual cells, is part of another system of support, tissue tension. It's the release of tissue tension that's forming this radish rose. You may have noticed that when you strip the skin off stems like rhubarb, it curls. This shows that the skin is under tension. What's more, if we separate the inner tissues, they immediately expand, showing that they were compressed and exerting a pressure. So the pressure exerted by the inner tissues puts the outer tissues under tension, and the firmness of non-woody organs depends not only on the turgor of individual cells, but also on the mutual tension of the tissues. Tissue tension helps the whole stem to withstand bending forces. The skin of this stem is under tension, and it's quite resistant to bending forces. But I've stripped off the outer layers of cells on one side, and now when these are uppermost, it's much less resistant. In effect, tissue tension pre-stresses the outer cells, and I can demonstrate how that improves resistance to bending. Now, these two pieces of elastic represent the outer layers of cells on a stem, and if I apply a bending force, over here the cells are in tension, and here they're compressed. Now remember, cellulose is good under tension, but poor under compression. And if I apply more bending force, of course, it buckles. But now, if we put those outer layers under tension, pre-stressing them, now if I apply the same bending force, instead of compressing these cells, it simply reduces the inbuilt tension. Pre-stressing, then, reduces the inherent weakness of cellulose to withstand compressive forces due to bending. So, for non-woody and growing cells with cellulose cell walls, it's turgor and tissue tension that provide support. But there is a third, very important method of support in plants, by means of specialized thick-walled support cells. These cells can be made even stronger by adding a new material to their walls, lignin. And it's lignin that makes plants woody. Lignified material resists compression extremely well, and the reason that wood is so strong is because it combines two materials, rather like fiberglass. The cellulose provides tensile strength like the glass fibers, and the lignin gives the hardness and the stiffness, the resistance to compressive forces of the resin. The remarkable thing is that the structural needs of plants are met by deploying these two materials in just 6 basic cell types. But to see how that's done, we need the microscope. Simple hand sectioning is quite adequate for a first look at soft tissues. And I can demonstrate how with this young mint plant, where I've stripped off the outer leaves on the topmost bit. The trick is to slice quickly with a wet razor blade, preferably one-sided, trying to get a thin section of tissue, ideally 1 cell thick. But there's no hope of doing that all the way across the stem. The best we can hope for is a section where part, perhaps only 1/4 or half, is sufficiently thin to see the cells clearly. Then a paintbrush is useful to transfer those that look promising to a microscope slide. Now just put on a cover slip, carefully so as not to trap too many air bubbles, and that's all there is to it. This is the sort of thing you see under low power, fuzzy in places because it's too thick, but the arrangement of the main tissues is clear. In the middle is the pith, made of parenchyma cells with cellulose walls. These are living, all-purpose packing cells. In close-up, you can see they have uniformly thin walls, with air spaces between the cells at the corners. The 4 darker areas at the outer edge of the pith are the vascular bundles, or veins, which are concerned with transport. They're the plumbing system. Nearer the outside are smaller parenchyma cells making up the cortex, which is green because chloroplasts are present. The outer cell layer is the epidermis, and it's tension in this layer that gives rise to tissue tension. Finally, at the corners, there's a specialized support tissue, collenchyma. The cellulose walls of these living cells, which appear white here, are thickened at the corners. This scanning electron micrograph shows the characteristic thickened corners very clearly, but notice that the side walls are still thin, which is typical of living, growing cells. Collenchyma cells can elongate and grow just like parenchyma, which is why they're used for support in young growing organs. You can see more detail in the vascular bundle of this section of mint stem because it's thinner, properly fixed and stained, and not cut by hand. There are 3 different tissues in the bundles. In the middle is the cambium. Cambium cells look flattened and form regular files because these are dividing cells. To the inside, new cells differentiate to form xylem tissue. To the outside, phloem tissue. Both these tissues contain a mixture of cells, including xylem parenchyma and phloem parenchyma, but the most important cells are those specialized for transport. In phloem tissue, these are often difficult to see, except in climbing plants. This cross-section of a clematis stem shows the main phloem transport cells, sieve tubes. You can recognize them where the section shows that they're closely linked to smaller companion cells. Sieve tubes are living, quite delicate cells with cellulose walls. They transport sugar solution from leaves to other parts of the plant. In longitudinal section, you can see they're long cells, and in this high-power view, there's a characteristic feature visible, the sieve plate. This is a cross wall, seen obliquely here, with perforations that allow solutions to flow from one sieve tube to the next. Xylem, on the other hand, is a tough tissue, where the cells have thick walls which become lignified, as indicated by the red stain here. And as they mature, the cells lose their cytoplasm and die. The large cells are xylem vessels, which are wide and very long. You can see this more clearly in longitudinal section. This one is through an older mint stem which has stopped growing, and the cells have reached their full size. The xylem vessels are the cells with patterned walls. These long vessels are formed by several cells losing their cross walls and fusing end to end. They transport water from roots to leaves, and because of their lignified walls, they also have a support function. The wall patterns reflect different types of lignified thickening. These pitted vessels, where the walls are completely woody except for the pits, occur only in mature, non-growing tissue. The pits act as channels that allow some sideways movement of water in the xylem. Before pitted vessels develop, you get vessels with spiral or ring-like annular thickening, as on the left. This shows up well in scanning electron micrographs. These are the only kinds of xylem vessels present in growing tissues, and the reason is that this type of thickening allows some elongation. Rather like this. Now look again at the young mint stem and consider the overall distribution of specialized support cells. The 4 groups of collenchyma cells at the outer corners are the most important. Xylem on the inside of the vascular bundles gives some support too. This symmetrical arrangement of strong cells around the outside of the stem gives good resistance to bending forces. Compare this with a mature mint stem, which is much stronger and tougher, but can no longer grow. It's basically similar, but the vascular bundles are larger with more xylem, which is more heavily lignified. There's also an obvious dark ring at the inner edge of the cortex, and these cells function purely for support. They are sclerenchyma fibers. These are long, narrow cells, and in this longitudinal section you can see that the sclerenchyma fibers have overlapping pointed ends that mesh closely together. Their thick cell walls, seen here in transverse section, are heavily lignified. So like xylem vessels, they are dead when mature. The close packing and thick walls of sclerenchyma fibers mean that they form a very strong tissue. It's as though steel supporting rods were inserted in the stem. And they're an important component in xylem tissue. Here you see large vessels surrounded by strengthening xylem fibers. But it's mainly the outer ring of sclerenchyma fibers that makes the older mint stem so much tougher and stronger than the young stem. Indeed, it's the strength and length of sclerenchyma fibers that makes sisal, jute and hemp such useful materials for ropes and string. An outer band of sclerenchyma fibres is very common in grass stems, giving them a strong tubular structure which is able to survive bending forces with the minimal use of strengthening cells. If you've ever tried to break even quite a small grass stem, you can probably appreciate just how strong those sclerenchyma fibres are. Such a stem, strengthened by fibres towards the outside, can be a remarkably strong structure. The length to width ratio can be as high as 500 to 1, which means that if this were a metre wide, it would be 500 metres tall. Such simple, often hollow tubular structures are light and extremely efficient in their use of materials. They use the minimum amount of cellulose and lignin to achieve their strength. For a plant like grass, which dies back each year, economic use of lignin is important because it takes a lot of chemical energy to make it. But there's a problem if the grass is very tall. A short stem can resist bending forces, but as it lengthens, it will bend more in the wind, and eventually it fails by buckling. Yet plants like bamboo, which is a grass and retains the same kind of structure, can grow to heights of 120 feet, 40 meters. The secret lies in these nodes where the leaves emerge. In a split bamboo stem, you can see that it's not a simple tube. At the nodes, the stem is braced by plates. How do these help? Well, as a tube bends, its cross-section becomes more oval, and where the walls come closer together, the structure loses the ability to resist bending forces and fails by buckling. The plates help to retain the stiffening properties of the circular cross-section and so retard the onset of local buckling. Even so, bamboos represent the limit for hollow tubular structures. When plants grow still taller and carry a greater weight of leaves and branches, they experience much stronger bending forces in the wind, and they must have more woody tissue. Indeed, the trunk has to go on increasing in width as the tree grows taller, and it does this by a process called secondary thickening. Now, this is something that monocotyledonous plants like the bamboo and the other grasses can't do, but dicotyledonous plants like this tree can. Now, obviously, after a few years, the tree trunk is pretty well solid wood. So how does it get like this from being a seedling? And what is it that allows it to carry on increasing in width? Secondary thickening can occur even in plants like this sunflower, Helianthus, that dies after 1 year. In this young sunflower stem with dark caps of sclerenchyma fibres to the outside of each vascular bundle, the cambium is restricted to the bundle. Secondary thickening starts when the cambium extends sideways from these vascular bundles. In this older stem, the cambium has begun to do this, cutting off new secondary xylem to the inside and secondary phloem to the outside, so enlarging the vascular bundles. Here a complete ring of cambium has formed, linking up the vascular bundles, and eventually there will be a ring of secondary tissue, with the fibre caps of the original vascular bundles left behind as dark blobs. Now let's consider what happens in perennial plants that continue to grow year after year. In this log, annual rings chart the progress of secondary thickening, as they do in all woody plants that show seasonal growth, but they're much more obvious in some plants than others. This transverse section of an oak branch at high magnification shows why. There's a cyclic variation in the size of the xylem vessels, which appear white here. Again, in longitudinal section, you can see it's this change in vessel size that picks out the annual rings. But why are these annual rings present in the xylem? And what happens to the phloem? Each spring, the cambium becomes active again, forming more xylem tissue to the inside, which increases the stem diameter, and more phloem to the outside. But this new phloem squashes the old phloem from the previous year, so only the current year's phloem remains. Later in the year, as growth slows, the xylem vessels tend to be smaller, and it's the contrast between these autumn vessels and the large spring vessels of the next year that marks the annual rings. In this scanning electron micrograph of oak, the huge spring-form xylem vessels are seen embedded in smaller fibre cells. So wood is almost entirely composed of secondary xylem tissue, and it's the densely packed fibre cells that give wood its great strength. Now, so far, we've concentrated on stems and trunks, but other parts of plants have quite different functions, experience different mechanical stresses, and so have different structures. Leaves are the food factories of plants. Their main function is to intercept light and carry out photosynthesis. So they're usually thin and flat, and need to maintain this shape without tearing and crumpling in the wind. The flexible leaf stalk, or petiole, absorbs much of the wind's force, allowing the leaf to bend out of the way and present a smaller area to the wind. The flattened leaf blade is strengthened and supported by a network of veins, the vascular bundles. To strengthen the margin against tearing, there are often hems and gussets of strong, thick-walled fibre cells. In this transverse section from a member of the lily family, you can see that fibres reinforce the edge like the hem of a handkerchief. And here you can see how the gussets of strong reinforcing fibres prevent tearing at the highly stressed junctions between the lobes of a leaf. So far, I've talked about plants where the most severe mechanical stresses are caused directly or indirectly by the wind. But this isn't always so. Different environments create different problems with different solutions. For this giant water lily, wind usually causes no problem. The water bears the weight of the leaf, which is buoyant like a cork. The petioles will be quite unable to stay upright and support the leaf blade in air, because their structure is very different from that in land plants. Firstly, a large part of the tissue in water plants is just air. There are giant air spaces between the cells. The name parenchyma is given to this sort of tissue. Secondly, ignoring the red blobs, which are not fibre cells, you can see that there are virtually no specialised support cells. Only a small amount of xylem tissue, which is near the centre where it has little stiffening effect. Another consequence of having so few woody cells is that petioles of water plants are often extraordinarily flexible. You can bend them into a circle and almost tie them in knots before they snap. There could hardly be a greater contrast between the environment of these plants and that of the desert. Desert plants face high temperatures and shortage of water, and the need to protect slow-growing shoots from grazing animals. Dense silvery hairs reflect sunlight and so help to keep the plants cooler. Many desert plants like this agave have a very high fibre content. Fibres stiffen the plant and minimise distortion and consequently internal structural damage during the long periods when turgor is low. Dark green-stained fibres make up a large part of this leaf section of the desert plant Nulinia. And the stomatal pores are sunk in deep pits, which reduces the rate of evaporation through the pores. So this structural adaptation helps to reduce water loss. Well, if I had to live in the scorching desert, I'd try to find somewhere keeping out of the sun. And that's just what these aptly called stone plants, lithops, do. In the desert, they'd scarcely show above the surface. But while that keeps them out of the sun, like all plants, they still need sunlight for photosynthesis. So they have a structural solution, a translucent core, in effect their own version of fibre optics that channels light down to their photosynthetic pigments below ground, a process we can reverse.